Now that everybody's got a calculator, our goal today is to try to attach a number. I want to introduce a couple of terms that maybe you've heard before. Do you guys know the term quantitative versus qualitative? I know on your guys' diagram this isn't in color, but on this one here it is in color. If I were to ask you to give me a qualitative description of this glass right here, you might say it's light pink. That's a quality. Does that make sense? Whereas this glass right here, if I asked you a qualitative description of it, you might say it's really dark red. If this was Kool-Aid, I think I gave you guys the example of my wife's grandparents making Kool-Aid. This is like barely Kool-Aid. Like this is taking water and adding like a little bit of juice crystals in and saying, here, have some Kool-Aid. It's really water. Right? Whereas over here, whoever made this Kool-Aid, would you like some diabetes with that? Yeah, like that's a lot of sugar in there. Okay. What we'd like to do today is attach a number to how, and the word we're going to use is concentrated. How concentrated a solution is. Maybe a synonym for concentrated would be how thick the solution is. Okay, but I want to make sure we use terms correctly. Strong is actually different. So you know, like maybe you make juice and you say, "Whoa, that's strong." In terms of chemistry, we use strong in a different context. Strong is about how much it conducts electricity, which is completely something different. Okay. So weak means things don't conduct electricity. Strong means they do conduct electricity. So try not to use those words if you can. The words we're going to use instead are dilute and concentrated. So dilute, if you want to use the word weak, you'd say it's a really weak thing of Kool-Aid. But weak is not the term we want to use. Strong is concentrated, but try to not use those words.
So if you had like really rank Kool-Aid, you'd be like, this is really concentrated Kool-Aid.
Yeah, that's what you'd want to use. That's the science term we're going to use from now on. Rank. Okay, so here's one of the ways in which we can try to quantify how concentrated a solution is. Okay. We use something called moles per liter, and this is by far the most common method of trying to quantify how, I don't want to use the word strong, so how concentrated something is. Do you guys remember what moles are? Okay, so a mole is basically a certain number of atoms. It's a lot of atom. It's at 6.02 times 10 to the 23 atoms. So basically what I'm asking you to calculate is how many atoms are there in a liter of probably water. It doesn't have to be water because like I said in the last yesterday, not all solutions involve water and solid stuff, but chances are it's water and solid stuff. So we need to try to figure out how many moles per liter there are. By the way, sometimes we abbreviate it as capital M. That refers to like, we call this molarity. Molarity. So let me do some examples with you on this. So here's my first question. How concentrated is a solution if we take 5.6 moles of NaCl and put it in 20.8 liters of water? This actually is a really simple one-step question. If you're trying to look for your molarity, it's equal to like moles per liter. So I have 5.6 moles. I have 20.8 liters. That's all you gotta do, just take the two numbers and divide them. All right. I just want to make a point, just in case not everyone's heard this from me before. When you divide these numbers, you're going to get an irrational, well, it's not irrational, but it's going to seem like an irrational number because it's just going to keep going for forever. At some point, you have to round. Do you guys remember the rules of significant digits, if I haven't shown you before? In case you don't, the basic rule is that this right here has 3 digits. This one right here has 2 digits. So we go with 2 digits. So the 0 in front, by the way, does not count as a digit because you could write this as like 0005.6 moles. you could write this as 0.000000208 liters. You can always have zeros in front of a number, so those don't matter. So you're going to count this 2. That's your first digit. You're going to count this 6. But then since this digit here is a 9, 9 means you're going to round up. So the answer we're going to go with is 0.27 moles per liter. Or if you want to, it's valid to write it as 0.27 capital M. And that's that numerical ranking based on how concentrated, not strong, but yes, strong, how concentrated a solution is. Does that make sense? As a general rule of thumb, I don't really want to write this down somewhere, but anything that is over 1 molarity is usually considered to be quite concentrated. There actually is an uppermost limit for most solutions as to how thick you can actually make them. If you use the juice example, at some point if you pour more and more juice crystals in and try to stir it up, you're not actually adding anything more that dissolves. You're just getting like a lump of sugar at the bottom. It's not actually making the solution any more thick, if that makes sense. So there is usually an upper limit. A general rule of thumb, anything that gets to about 10 to 20 moles per liter is about like the capacity. We actually have a term for that. It's called saturation. I think Peter, you mentioned it yesterday. You know that word? We're going to talk all about saturation on Thursday. But basically, most solutions have like an uppermost limit as to how much you can actually dissolve inside of them. So, that first example makes sense? Okay. Okay, let's try another one here. We want to find the concentration if we have 24.6 grams dissolved in liters. Okay, here's my first problem. If molarity is supposed to be moles per liter, I have the liters. I have 4.00 liters here, but I don't have moles. Do you guys remember how to convert a gram to a mole? Divide what?
A gram to a mole.
Gram to a mole. You need to use molar mass. Yeah, this is why we needed to review this before we started things. So, second quick review. NaOH. Do you guys remember how to find a molar mass of NaOH?
Sodium with an oxygen.
Okay, so sodium. Anyone know its number off the periodic table? Good. 2299. Oxygen is 1600. And that one's 1.01. Sodium hydroxide is one of the most useful chemicals to work with when it comes to molar mass because the number is exactly 40. It's actually 40.00 though, because all of these guys had 2 decimal places, 2 decimal places, and 2 decimal places. So even though your calculator is going to say 40, it's 40.00. And it's that many grams in a mole. I want to show you 2 ways that you could do this then. You could take 24.6 grams and you could multiply by 40 grams in a mole. Or you could try to take 24.6 grams and then flip the fraction and make it a mole over 40 grams. Which one's right? The bottom one's correct. Does that make sense? Here, this gram and this gram right here, they won't cancel each other. So we're not multiplying. You see how the grams right here will cancel though? So what we have to do is take 24.6. You could times by 1 mole. It's kind of implied there's a 1 right there, but you don't have to write the 1. Really, you have to divide these numbers. So I got 0.615. And now that I finally have moles, now I can plug that back up here and do 0.615 moles over liters. And then with 3 significant digits, I got 0.154. Let me know if you don't get that number. Does that make sense? So, if we're going to try to measure things as to how many moles, which is really just a whole bunch of molecules, you put in a liter. sometimes I'll give you moles, but if I don't give you a number in moles, we don't usually measure stuff in moles. We measure it in grams, right? Like we're gonna go to the scale in my back room there, measure things in grams. Then we have to convert it to moles first, and then once we've converted to moles, then we can actually do our calculation. Okay. Sometimes we can go backwards. Here I'm going to give you information, and our goal is actually to solve for mass. What I've given you here is a volume, and I've also given you a concentration, and our job is to go backwards. Okay. If you're good at looking at units, that'll really help. Earlier today, for those of you in my physics class, I was really trying to show how like volts is equal to like, what was it, like newtons over coulombs kind of thing there. It's really worthwhile to look at your units a lot. Okay. Watch what happens here. If I take 2.00 liters and I multiply by 0.150 moles per liter, what would happen to your units? Yeah. Does that make sense? Now I have moles. Actually, don't actually type that in yet. I want to do one more step here. I need to get to grams because it asks for mass. So I'm at this point right here, I have moles. What I really need to do is get rid of moles and put grams on top. Ah, there's a good question. We need to find that number. How do we find a grams per mole number? What's that called again?
Molar mass.
Right, molar mass. Molar mass of what? Silver nitrate. So let's look up silver nitrate's molar mass off to the side. Anybody know what silver's number is? Good, 107.87. Nitrogen. Okay. And then oxygen we're going to need 3 of. Oxygen is 16, but I need 3 of them. $169.88 is what I got. So let's go back to the start of my question here. I had liters and moles per liter. See how my liters and moles per liter could cancel? I have moles now. Well, now I actually have a grams per mole number. If I put the 169.88 right here, do you guys see how this moles right here will cancel with this moles right here? And in terms of my units, this liter will cancel with that liter. This mole will cancel with this mole. What's the only unit I have left? That's what we wanted. We wanted mass. So take 2 times by 0.150 and times by that molar mass. But do it all in one step. Rather than do it in stages, do it all in one step. Yeah, I got 50.964. In terms of significant digits, though, you only get 3. It'd have to be 51.0 because you get to keep the 5, you get to keep the 0, you get to keep the 9, but the 6 would round up. Does that make sense? So then the 6 would round this up from a 9 to a 10. So then this is where like the 10 is right there. That makes sense. This is actually a really typical question that I would ask you in a lab setting, because 51.0 grams is something that we have the ability to measure because all I have to do is go to the scale and put 51 grams on a scale. So it's often very useful to solve for grams. Does that make sense? Cool. All right, let's try another one here. You go to the back of my lab and you find a bottle that says that ammonia has a concentration of 14.8 moles per liter. First thing I want to point out is 14.8 moles per liter is really thick, really concentrated. That's like about as, I shouldn't use the word strong, but it's about as strong as you can make something. Usually the upper limit is about 15, maybe 16. The most I've ever heard of is about 18. At that point here, it's impossible to dissolve any more solid stuff. It doesn't happen. So, I also tell you that we have a bottle that's 2.5 liters. Our goal is to find the chemical amount of ammonia. Do you guys know what chemical amount refers to? It actually refers to moles. chemical amount, if you ever get asked to solve for that, it refers to how many moles is there. So if I'm asking you to find how many moles there is, how do I put these numbers together? That'll work, yeah. I'm going to do it the other way around if that's okay. I'll do 2.5 times by 14.8. I'm hoping that you can see how this works. See how that liter on the bottom will cancel with that liter right there? It's kind of like saying that you worked for 12 hours and you got paid $15 per hour. Does that make sense, that analogy? So 2.5 times 14.8. I got 37 right on the dot. So far, so good? Okay, there's another way that you can measure concentration, not as capital M in moles per liter. This one is called a parts per million. Anybody ever heard of this before?
Yeah.
Any of you have like a well or something like that, where like you have to test maybe like the iron concentration in a well? Heard that before? The back of like a water bottle, if you buy like filtered water, they often test the parts per million. Parts per million are very, very, very small amounts of concentration. Here, Rob. Okay. The idea behind parts per million is that it would be like 1 drop of water in a bathtub. Like it's hardly noticeable. It's very, very, very minute, very small. So here's something you might want to write down on your data sheet somewhere. A part per million is equal to a milligram per a liter. A milligram per liter is a part per million. Write this down somewhere so that you have it nearby. Milligrams per liter. Hello. So let's try an example here. I want to figure out how much mass of chlorine would be present if in 5 liters it says there's 6 parts per million. Parts per million is kind of a weird unit though. So what did I just tell you parts per million is also equivalent to? Milligram per liter. So kind of like what I was doing in the last examples here, how do I make it so that I can find a mass? How do I take this number and get a mass? What should I do with them? Cancel out the liters, yeah, by timesing them together. So it might look like this. 5 liters multiplied by 6 milligrams per liter, and you see how the liters will cancel? So what am I left with? 5 times 6 is 30. What are my units in though? Yeah, milligrams, yeah. One of the things I really want you guys to be able to focus on is watch your units really carefully, because that's kind of the whole point here is if you can make this guy and this guy cancel, you can solve for what you're looking for. There really aren't formulas in chemistry very often. Chemistry is not really a formula kind of thing, not like physics is. But if you understand how to put units together properly, you can solve a lot of different questions. Now let's try another one here. Let's say that you get a bottle of sparkling water and it tells you there's 440 parts per million. How much mass would there be in 200 milliliters? So again, what does parts per million refer to? How many milligrams there are in a liter. Okay, now this guy right here is not in liters. How do I convert milliliters to liters? Anybody know? Good. It's divided by 1,000. Yeah, there's 1,000 milliliters in a liter. So this guy right here is actually 0.2 liters because you've got to divide by 1,000 to get into liters. Well, now that I have liters and milligrams per liter, times them together. Take 440 milligrams per liter times by 0.2 liters. You see how those cancel? Yeah, I got 88 as well. Is 88 correct though? That's what I was looking for. It's actually 0.0. Why 0.0? Good. You need 3 sig digs. This has 3 significant digits. This has 3 significant digits. This guy right here, the 88 your calculator tells you, only shows you 2. So you got to make sure you add a 0.0 on. So you'd get that many milligrams. Or I guess you could write it as 0.0880 grams if you wanted to. That makes sense? How are you guys doing so far? Let me know if you're not. You good? Okay. Okay. Oh yeah, there's a third method that's fairly common. This one you might see on like commercial products. Cleaners are a good example. Another great example is anything that's like a food or beverage often lists things as like a weight or volume percentage. Okay. And this one's really straightforward. If you want to do volume by percentage, you take the volume of the solute, you take the volume of the solution, you times by 100. Or if it's percent by mass, you take mass of solute, volume of solution times by 100. It may, like the formula kind of seems a little confusing to start with. I promise it's not actually that tough. Okay. The way we usually write it as a percentage as either V over V or W over V. So let me just show you an example. Let's say you have some acetic acid. You have 100 or you have 10 milliliters of acetic acid, and you dilute it to a total of 200 milliliters. We want to find the percent by volume. So here's what you do. You take 10 milliliters, you divide by 200 milliliters, you times by 100. No, it's not really. One of the things that happens here then is this milliliter and this milliliter, they kind of cancel each other. So 10 over 200 times 100. Yeah, 5%. In terms of sig digs though, it's going to have to be 5.00% because we need to have 3 sig digs. And maybe you'll see this if you buy like a cleaner or like vinegar is a good example. You go buy vinegar in the store. You might have some actually. Sometimes we keep some on hand. Never mind, I don't have any apparently. Sometimes you'll see things written as a percentage though. So this is basically how it works, is take the small amount, divide it by the big amount. It's really straightforward. That makes sense? Okay, one last thing and then I'll let us go for a bit of a break here. I want to combine what we did yesterday with what we're talking about today. Right here, this is a dissociation equation. Okay. Why is this dissociation not ionization? It's ionic, yeah. CaCl is ionic, but I've made a mistake here. CaCl is not appropriate. It should be CaCl2. I definitely screwed that up. One of the things I mentioned yesterday is that if this thing breaks into pieces, you're going to get 1 calcium, but you should have 2 chlorines. Here's how this applies to what we did today. Let's say that the concentration of CaCl2 is 1 mole per liter. Well, when it breaks up into pieces, this guy's concentration will also be 1 mole per liter. Because like a recipe, there's a 1 sitting right here, and there's a 1 sitting right here. Groundbreaking thing here. If there's a 2 sitting right here, it doubles. Does that make sense? What was that? That's not the way this works though. There's not a formula that says like this has to equal these guys right here. Okay? Because what this refers to is that, say what I just drew was 1 liter. Okay? What you used to have was a molecule that had 3 little things on it. And you might have had like say 1 of those. So like this is 1 mole in 1 liter. Let's say it breaks up into pieces. So now it's not like this. Now there's 1 of these guys and 2 of these guys. Well, now there's 1 of these in 1 liter, but there are 2 of these in 1 liter. That makes sense? Let me try that one more time then. See if I can try that again. Let me try to draw it a little bit better. Okay. Let me draw just a container here. Imagine that container is 1 liter. Okay. And inside, we're going to put a molecule of CaCl2. So let's pretend that this guy right here is the Ca, and that this guy right here is a Cl. Currently, there is 1 mole in 1 liter. Does that make sense? Let's say I break it apart. So same container, I'm not changing my container, but I break it apart. So now the white guy is sitting there, and then the black guys are sitting over there. How many of this guy is there? Well, there's 1 of them. So this guy, there is 1 mole in 1 liter. So even though this guy is a big molecule, this guy that's been split into pieces, there's still just 1 mole per liter. But these guys right here, now there are 2 of the black ones in 1 liter. So the concentration doubles. Let me give you another analogy. I'm big on analogies. My daughter, Kinzian, has a lot of toys. And so imagine that Kinzian has like a Lego type toy that has a bunch of like pieces on it. Okay? And imagine that she has 1 Lego toy sitting in the room, just in the middle of the room. All the Lego pieces are put together. I would say the concentration then is 1 Lego toy per room. So like 1 mole per liter. Does that make sense? Then let's say her little sister Cami comes along, and Cami likes to destroy things. Like she rips everything apart. So she finds the little Lego toy and she tears pieces off of it, and she scatters them around the room. Well, now the room looks a lot dirtier than it was before, doesn't it? Because there's like a little piece of Lego there, and a little piece of Lego there, and a little piece of Lego there. Is there anything more in the room though?
No.
Well, technically not. Like there's not more stuff in the room, but rather than it being one big object all stuck together, Cami scattered little pieces all over the room. So the concentration is going to look different, even though the actual number of pieces are still the same. Does that make sense? So rather than there being 1 big Lego piece per room, now there's 17 little Lego pieces per room. So the concentration is going to appear to go up. Does that make sense? Okay, so let me try an example on this. Let's say you have a 0.5 mole per liter solution of, that is aluminum sulfate. My question for you is, what's the concentration of the Al ions and the SO4 ions? So, first thing we got to do is I need to write a dissociation equation. Al2, SO4, 3. How will this thing dissociate? What's it going to break up into? Sure, an Al and an SO4. Now, if I'm notating this properly, though, I need a few more things than what I've just written. First, I should write aqueous after everything, because the state of matter is really important. I'm going to be very picky on that. Please don't skip that. Is it Al by itself? If it's Al by itself, it's solid. Well, actually, the charge on aluminum is 3+. What about the charge on sulfate? Hello. -2. -2. One more thing, is this thing balanced? We need a 2 in front of the Al, because there's 2 of them right here, right? 3 in front of the SO4. Okay. Now that I've written my equation, last step. This guy right here is 0.5 moles per liter. This is kind of like Kinsey's toy, where really there's 5 pieces to this toy. There's 2 aluminum pieces and there's 3 sulfate pieces, and they're all together. And so the toy in the middle of the room doesn't really seem like it's that messy. And now Hurricane Cami has come along and torn it into pieces. And so now there's 5 pieces scattered around the room. What's the concentration of this then? Well, it's twice as much. So if you have half and you double it, it's now good. Make it 1.0 though. You need 2 sig digs. And what about a 3 then? Good. 1.5. Yeah. Because really, from here to here is twice as big, and from here to here would be 3 times as big. It seems weird though, because you'd say to yourself, how in the world can 0.5 of something turn into 1 plus 1.5? But it's based on pieces. Let me diagram it. what we have here are 2 and 3. So right now we have one thing per liter, I guess. But then if it breaks up into pieces, now you have like 1, 2, 3, 4, 5. So this guy there's actually 2 of now. And this guy there's now actually 3 of instead. So the concentration doubles. But it doubles because you're splitting it into smaller pieces. All right. Any other questions? We'll work on it a bit. Okay, we have roughly over an hour left here. So now I want to flip the class here. Take 5-minute break. When you guys come back, I need you to practice some stuff. So here's some options for practice. There's a bunch of textbook questions.